Hi, everybody. Today we are going into the wide world of data mining. And over the next few lectures, what I'd like to do is talk about some of the common techniques in data mining. This is not meant to be exhaustive. There's a huge amount of literature on this. It is mostly intended to give you sort of a point of introduction into the study of data mining. And so you learn some of the techniques and methods for identifying a useful technique and then using it without actually getting kind of garbage out of the result. The work that I'm going to be presenting today is largely inspired by a couple of really good books. These are available through the library. There's an introduction to statistical learning by James et al. It comes in a Python implementation as well as an R implementation. And then there's this Statistics, Data Mining, and Machine Learning in Astronomy by Ivesic et al. And I think it's a good resource, particular for understanding some of the more data-oriented problems in the astrophysics side of the field. Now, when I talk about data mining, I want to note that we are moving in domain. A lot of what we've talked about in the class up to this point is the idea of hypothesis testing. You've collected some data and you want to use those data to understand whether something is true or to reach a physical conclusion. What we're talking about now is moving into a different world where we are thinking about hypothesis generation. And often this happens when you have a data set and you're trying to glean meaning from it, but you're not asking specific questions of that data set beforehand. As a result, this is extremely dangerous because it's very easy to use a data set and generate post hoc results. And these very readily fall into statistical pitfalls where we ascribe meaning to something that is just a natural consequence of statistical fluctuations. So what we need to think about when we're developing this is to avoid a lot of these where correlation does not equal causation, and post hoc reasoning, once you see your results, leads to hypotheses that you hadn't considered before. Complex data sets have many possible interpretations, and so this leads to it's very easy to kind of fall into a trap here. So we'll think a little bit more on traps later, but these are very useful if you're trying to understand experimental data. This is developing meaning, and you can use this to inspire hypotheses that you can then go out and construct specific tests for these. You can also use this to try to understand what is going on. These data mining techniques and tools are essential for a lot of the parts of experimental physics where we get a data set and we don't know what's driving a problem in it. What is leading to this noise signal? What is causing this little jitter in these results? You can use the techniques of data mining to identify those things that are correlated with it, and perhaps through experimentation you can then go forward and identify a cause, and then in the case of noise maybe remove that cause. So you improve your data set. So it's a very grand set of techniques for kind of asking data, but it's dangerous to do science on them. And you have to make sure that you're on a firm statistical footing if you use these techniques to reach conclusions. So I'm going to talk about three main techniques or approaches here. And the first one is trying to identify what are the driving variables that lead to an output. So this is, I'll describe this as describing the predictors of a variable. And the technique that I'm going to highlight here is called multiple linear regression. And this is it's a very simple method, which thinks about what happens if you have a bunch of independent variables. I'll denote them xij, where I is a datum and j is a variable, so it's a vector of measurements here. And we are just going to consider the response of a variable y as a function of those variables x, and we're going to assume a very simple functional form to get started, which is that it's a linear model. And so this is the ith dependent variable is an offset plus a bunch of slopes times the different possible predictor variables. And this is essentially fitting a hyperplane to these j-dimensional data space. And what you're looking for here is what the significant or strongest slopes are to tell you which variables are the most significant. In the language of data mining, I'll just note that this set of data, the ith measurement of the jth variable, is an element of what's called the design matrix. So if you see that in the literature, they're just talking about the underlying data set here. To explore the idea of multiple linear regression, I wanted to use some weather data. So these data come from the Edmonton International Airport weather station from 2013 to 2022. So right down the road from where I'm recording it. And what I've done is I've coded all of the data into a table here where I record like the day of the year, month, day, what year it is, the wind speed, the relative humidity, the wind direction here in tens of degrees. So 270 is wind out of the west at 270 degrees. Temperature in Celsius, pressure in kilopascals, which this seems a little low, but that's what's in the data set. And then the visibility measured here in kilometers. So this is oh, sorry, yeah, it's 101 is atmospheric pressure, so 93 is fine. Yeah, we're good. And so then this forms the design matrix, and then there's 1 hour every day for 10 years. So we have 100,000 data or so of these different measurements. And what we want to do is kind of explore this data set and identify some possible correlations. So for example, this is a plot of the temperature as a function of the day of the year, and you can see seasons in this graph. So 0 is January to December, and so it's warm in the summer and cool in the winter, and that's all pretty cool. But the thing that I'm really kind of curious about in this data set, and I'll set up our problem to consider, is what is the relative humidity here of a data set? Actually, I'm going to use this to explore this idea of what a dew point is. And I know that a dew point has something to do with how humid the air is and the air temperature. So this is a plot of the relative humidity over the course of the year. And you can sort of see there's some, annual variations that are kind of peaking in May. You get the largest scatter, and then again here in September. So these are kind of the dry periods of the year, I guess, or where you get dry data, but also some heavily saturated times as well. So that gives us the idea of this. Now, I'll stress that I don't know much about data, but I'm a physicist. And this, of course, brings together the fact that nothing is more annoying than a physicist trying to understand a field for the first time. And we are going to do literally the worst thing ever, which is just kind of understand all of meteorology by just, fitting some statistics and figure out how everything works. So what we want to do is figure out how does the dew point data relate to the other parts of my data table. And to give you an example of that, what we'll do is we read in, and I'm going to recommend here this package called Stats Models. It's a very statistically oriented data package. You also can use scikit-learn to do all of this, and I've only picked Stats Models because they have a nice output function. And we're going to sort of show that, and then I'll show you how this works in sklearn as well, or scikit-learn. Uh, so I import my data, import stats models, the API as SM. I read in the data, I drop anything that has missing values. So I need to make sure that it's fully complete data set. And then I'm going to make my responding variable the dew point temperature. And then because I'm fitting a linear model, I say, okay, I need to include an offset term for my linear model. So it allows the B term to be non-zero. And then I set up a stats model ordinary least squares regressor of this um, response variable and then the design matrix. I fit that and then I print out a summary. So that gives me the tools that I need, and the results, as I said, I got them because they're pretty. Here's what comes out. It's this big old table of what we're looking at, and I want to predict the dew point in degrees Celsius. It tells me that once I drop all my missing data, I have about 85,000 data. You can see when I ran my stats and everything, some R squared values, all that. This is very high correlation, so it means we're doing a good job of predicting the outcome. So this is the R squared statistic. Some other things, if I want to compare one fit to another fit, it's very useful. But the thing I want you to pay attention to is this block of text down here. In particular, this gives the value you measure for something like the constant. This is the B term, the offset here. It's associated uncertainty. And then we also have the day of the year, month, day, year, relatives, the wind speed, relative humidity, direction, temperature, and station pressure. And so what you're looking at is the coefficient and the associated uncertainty of this from just the covariance matrix of the result. And it nicely gets summarized here in a t statistic, which is just basically the coefficient divided by the standard error. And you're looking for large values here because that means that there is a strong and significant correlation with with that parameter. And what's neat is you identify very quickly that there's two large numbers here: the relative humidity and the temperature. This shows you the basically the corresponding credible ranges, central 95% of the fit, and then the probability of drawing that t statistic under a very restrictive set of normal errors, Clay analysis, for, basically, do the ordinary least squares requirements hold? If so, then you get a probability, and so 0 means there's significance. Even so, I don't know that I'd necessarily, like, this is only a 2.8 sigma result, and so formally that's like a 99.5 consequent or probability of false alarm. But we're in physics. We don't trust a 2.8 sigma result unless we have very well understood data. Here, we don't understand the data. So highlighting a few things here, we notice that there are these two extremely strong predictors, the relative humidity and the temperature. That has something to do with the dew point. I think high humidity, both of those things vary with the temperature. And then you also have a bunch of things that don't seem as important, day of year, the month, or the atmospheric pressure. So this is what multilinear regression is really useful for. It identifies those factors that are predicting the dew point for the data set. So says relative humidity and the station temperature. And so that gives a sense. I also want to note this. The condition number is large, and it might indicate strong multicolinearity or other numerical problems. This is something to pay attention to. We're going to come back to this in a moment. But notice this statement about multicolinearity, which is important in these high-dimensional data sets. All right, so we can go and take a look at relative humidity and temperature. here. And you can get a sense of this by looking at how the dew point varies as a function of temperature and relative humidity. And this sure shows, okay, well, the dew point and the temperature have a strong correlation with some scatter result here. And then there's also this, fairly significant structure in the relative humidity data here. So that also correlates with the dew point. And what you can do is go back to the coefficients here and take the relative humidity times 0.24 plus the temperature times 0.94. And if you take those two, you can create a predictor variable, 94 times the temperature plus 24 times the relative humidity. And that turns out to give you a very nice correlation with some scatter down here. But it's a good tight result. And this combination of these two factors is a better predictor than the individual variables by themselves. And so this multilinear regression gives us a nice technique to sort of figure out, well, these are the important factors. And sure enough, if you then go onto Wikipedia and you look up what a dew point is, you discover that that has something to do with like the Clausius-Clapeyron relations and the saturated vapor pressure, or the vapor pressure of water in the Earth's atmosphere, and the temperature at which it's going to reach, it's going to condense out given a certain temperature. So these all should be the most tightly related variables, given how this works. But this weather station data allows us to kind of infer what the factors are without knowing anything about meteorology, just a little bit of linear fitting, and that can tell us how it connects up. Now, to come back, let's think about this multicolinearity idea. When you have just an XY fit, you don't worry about this. But once you introduce multiple X values, your design matrix has multiple components, raises the question, what happens if those variables are correlated with each other? So if we have this model where y is b plus m1 x1 plus m2 x2, what happens if x1 and x2 are correlated with each other? I mean, what if they're the same variable, just that got in there twice? Well, then m1 and m2 can't be distinguished from each other. So if I increased m1, I would decrease m2, and I'd get an equivalently good fit. And so one way we can do this is actually check to see how the variables in my design matrix are correlated with each other. So with this, it's a small enough data set, I can actually just go pairwise and measure every pair of variables and construct the Spearman correlation coefficient between those data. And I get a little matrix that looks like this, where you have each variable along the, each variable on the x and y. So the diagonal is a variable correlated with itself. Sure enough, that really better be 1 if a variable is correlated with itself. 0 means there's not much correlation. So for example, the day variable and the year variable, not correlated with each other. They're different units of time, so there's not much correlation there. You'll notice that the month and the day of the year are correlated with each other because the day of the year scales with the month. So that all makes sense. So this is the rough correlation structure. The interesting parts are the rest of the design matrix down here, where you find some weird results. Like, look at this. Visibility and the year are kind of correlated with each other. That's weird. Maybe there's some sort of basic behavior with that. And sure enough, if you actually look at the data, what I've done here is I've plotted the year data and then the visibility, and I've just added a little random number to each of these discrete variables so you can kind of see the block. And yeah, for some reason, the visibility at the airport, you can see the concentration of the data increases. And so there is this positive correlation of visibility over time at the airport. Who knows exactly what was going on? Could be long-term variations, fire seasons or something like that, giving you this variable. Maybe they recalibrated their sensors, something like that. Who knows, but it is there in the data set. So it does make sense that everything is going on here. But remember, we were predicting the dew point, and so there is this correlation here that's significant between the temperature and the relative humidity. So as the temperature goes up, the relative humidity goes down. And you can kind of see that here, where the temperature peaks in the middle of the year, but it also has those increases are associated with the very low humidity days. So it does kind of make sense that this correlation's in here, but that's gonna mess with our regression. And it does mean that the confidence that we have in the individual coefficients for these two, the relative humidity coefficient and the temperature coefficient, those are probably stronger than they should be, because an increase in temperature can be is correlated with a decrease in relative humidity, and so that's going to cause those two coefficients to not necessarily be independent of each other. So this provides one way of understanding the idea of multicollinearity. And when you see this and you get that multicollinearity warning, you should just make sure that you're not paying strong attention to the absolute values of the coefficients. Their relative values and the groups of data that are correlated with each other all can kind of move in lockstep and be a block of relevant information, but you should not treat any single one of those values as, this is the truth. You can instead look at it and think, oh, okay, well, this has something to do, something in this block of constants has something to do with my responding variable. So I can pay attention and investigate. So remember, hypothesis generation gives us something to look for, but it doesn't necessarily prove definitively that something is true. Another way of calculating multicollinearity is called the variance inflation factor. And so what you do here is essentially you create that correlation. You do the fit to the data using everything but one of the variables. So the variance inflation factor here is measured as 1 over 1 minus the r squared value for the fit without the jth datum. So this is kind of supposed to indicate you correlate xj with all the other predictors. And if that's a strong correlation, this r is going to be large and the variance inflation factor is going to go up. And the warning here is if your VIF is larger than about 5, you should pay attention to your data set and recognize that there are correlated data within there. So stats models checks this. There's a package called the variance inflation factor. And so what we can do is just sort of loop over all the different values here and ask what the VIF is for them. And they're all, this is a messy data set. Everything is kind of correlated. You can see that the temperature and the wind speed don't have a lot of correlations with the other things in the data set. So you can therefore kind of pick out and say, well, these things will be good, but the other things in the data set I have to be careful with. And so one thing you can do is start to remove variables from your data set to reduce multicollinearity, so you just get independent results. But just be aware of this multicollinearity because it undermines your ability to interpret individual coefficients in your fits. The next thing to talk about is nonlinear relations. Not everything is a linear model. So what you can do is you move to this space called generalized linear models, or GLMs. We are assuming, kind of Bayesian-like, that y is the responding variable is distributed as a normal, where the mean varies as a function of all these other coefficients, and then there's some associated variance for the underlying data set. What we want to do in a GLM is to assume that the mean doesn't necessarily follow, or that the data don't necessarily follow a normal distribution here, but that you instead have other distributions like the Poisson or the de Bernoulli distribution, and those means follow this linear model. And we say that, okay, there is some complicated function where I figure out what the sort of central value of the data are, and this is that linear model, but then I transform that result using this linking function called eta, and sort of map it onto a different distribution or possibly a nonlinear variation of the central value of that distribution. That's a very abstract way of putting it. One thing that we want to do is often logistic regression. And this is really useful when your variables are binary, sort of true, false kind of data. And this shows up for my field all the time because there's often a question of whether a source is detected in our data set or not. So it's this censoring problem of whether a star is actually visible and what are the properties that determine whether that star is present in the data or not. That follows a logistic regression model where the expectation of whether I see something in a model, sort of the mean value of finding it, which is the p-value of a Bernoulli distribution, is predicted as some linear model of a bunch of other things: the noise in the underlying noise in the data set, the brightness of the sky, etc. Those are all factors that go into this model, and then we use this logistic function regression, which is you exponentiate that linear model, and then you divide over 1 plus. So this ranges between 0 if this coefficient is negative and large, and then as it becomes positive, this converges to 1. So it basically switches between a 0 and a 1. And then we use this Bernoulli distribution to actually match to the data, and we get a nice kind of detection testing framework. Now, all of this has kind of given us like tools for measuring the different coefficients. What we can do is actually use this, and this is very useful in very large data sets. We actually pick out what data are driving. And this is the process of variable selection. So if you have our dew point measurements, can we actually zero out one of the relative humidity or the temperature and just say, well, the best predictor here is just the temperature independent of the relative humidity, or do we need both terms? And the general idea behind variable selection in this linear model case is to do regression, except what we do is we minimize this whole term here. So what this is that this first term is the chi-squared light term. It's the difference between the observed data and the linear model, so y minus the offset minus the slopes times the data. So this is y minus b minus mx, and then squared because it's kind of the chi-squared light term. The interesting term here is this other one, where there's a tuning parameter alpha, and then we sum over the variables of the absolute value of the coefficients raised to some value here that's called p. So p is you choose it for this method. So if p is equal to 1, so it's equal to the absolute value of the sum of the coefficients, This becomes the least absolute shrinkage and selection operator, or LASSO. I just wrote down LASS, but this is LASSO is the name of the tool. And then if p equals 2, this is a different variable selection technique called ridge regression. And essentially what this is doing is it's adding a penalty for terms with non-zero or large coefficients. And this general process is we are messing with our goodness of fit statistic by adding on an extra term. And this is just called regularization. So whenever you see anyone in artificial intelligence and machine learning discussing regularization, all they're doing is they're messing with chi-squared to kind of get the behavior that they want out of a model. Regularization is just a fancy word to do something that sounds like a statistical abomination. But it gives us a method to kind of approach this, and there's a technique that we can use to make sure that we are not messing with it too much. First, I note that this really only works if the relative scales of the data along the different variables are equal to each other. So notice that pressure is on a very different physical scale than the wind speed or the day of year. All of these have different ranges of the data. So what we want to do is we scale the data. And we take each vector of data, and for a given datum, we subtract off the mean for that data and divide by the standard deviation. So essentially, this is transforming to a z-score. So it's, for the relative humidity, I take off the mean relative humidity and then divide by the standard deviation. So this puts everything, if these were Gaussian distributions, this would put them into sigma units. So it moves from some value becomes, this is just plus 3 sigma or minus 2 sigma. In the scikit-learn package, this is sklearn. You import the standard scalar and you just scale the data, scalar.fit transform of my raw data. Gives me my scale data. So it's a nice little one-liner because this is a very common operation. I'll note that we can do exactly what we did before the linear regression model by importing the linear model, doing a linear regression, and fitting the scaled data. You can find the coefficients and the intercept just by spitting out those results. They will give you the exact same results as the stats models. It's the same underlying math. The big difference is that this is prettier, but once you know what to look for, you can stay entirely within the scikit-learn environment. Nice thing about scikit-learn is it gives us the ridge and the LASSO models respectively, and you can do the same thing, just fit the scaled data and figure out what the coefficients and the intercepts are for those two methods. And if you do that, you come up with these results here. So the numbers are a little different because we're using the scaled data and not the original data set. And when we're doing, again, if we're doing ridge and lasso regression, we want to be making sure we're treating the variables equally because this regularization term depends on the value of the slopes. And if my data scale is different, then the slope values will be different. And I'll end up paying more attention to something measured in meters compared to something measured in kilometers. And those are physically meaningless. So we use the standard scale data, and so the coefficients come out different. Nonetheless, we get a significant values for relative humidity scaling and temperature scaling in the regular linear model, as we expected earlier. And then small values indicate that, oh, this isn't very significant. And what I want to call your attention to is that the ridge values maintain the same as the linear model values, but it reduces the effects of these other kind of more nuisance variables, the day of year or the day, of the month. Those all kind of decrease a little bit in scale. But what's neat is if I look at the lasso regression, it zeroes everything out except for those two coefficients that we looked at earlier, relative humidity and the temperature. So it really just works. It says these are the variables that matter because it's penalizing something that is having a, small but non-zero effect, gets penalized under LASSO. Now, if you go and you look, what I've done is I've picked a value of alpha that's equal to 1, and that in my regression coefficients, or my regularization term, means setting this alpha term to 1. I just picked that ad hoc, and that sort of said, this is how important I think the penalty is. That's not very well motivated. I picked a value and I'll actually change what my slopes are and what variables are included if I change my alpha value. So we need a method for not picking this ad hoc. And the way the tool we'll use is something that's called cross-validation. And what this allows us to do is to pick a regularization parameter robustly. The way that we can do this sort of most easily is called n-fold cross-validation. And what we're going to do is we're going to fit the data, but we're going to kind of keep some of the original data in reserve. We have 85,000 data points, and we just kind of want to leave a fifth of those. That's because it's 5-fold. We'll leave a fifth of those on the side and come back and test this. But of course, we want all of those incorporated in our data, so we'll just rotate in blocks of 1/5 what we're sort of holding out from our regression. And this method is called cross-validation. So we're going to do the fit 5 times using different subsets of the data. And when we do that, we're going to find for a given set of data called the training data, we're going to measure the coefficients for our fit for a given value of the regularization parameter. And from there, we're going to predict the mean standard error on the validation data. So that's going to be what we've left behind. We use those coefficients and we see how well this models us. And then for those 5 different subsets, we're going to calculate the average mean standard error for the fit. And essentially we're going to say we're picking the value that leads to the lowest mean standard error across these 5 different permutations of what's in and what's out of the data. And we're going to check that as a function of alpha, and we're going to pick an optimal value of alpha as the value that leads to the least standard error in the fit. And so this means it is least dependent on what is in versus out of the training data versus the testing or the validation data. And so that's how we pick our alpha value. The methods that we use, they're just given the little variables CV. So this is ridge with cross-validation and lasso with cross-validation. And you just feed them in there and it does a bunch of fits, but it picks the right value of alpha. And if you do that, you get values that actually look a little bit better. You'll notice when we just did straight up lasso, we end up with substantially different coefficients for the humidity and the temperature. But with cross-validation, you'll notice that the relative humidity and the temperature actually are quite close to just the linear regression model. And then there's some very small values of these coefficients here that kind of get suppressed through the lasso approach. Ridge does that to a little bit of a lesser degree, but lasso is a sort of a stronger variable selection method. Okay, so what we've done today in this lecture is kind of talk about how we pick features that predict an output variable. If we have a bunch of inputs and we need to find out what's driving that response, you can identify through correlation analysis what could possibly be there. So remember, this is not a test or a proof that that is what's doing it. You are simply identifying things that are represent this correlation structure and how important they are. So this is driving hypotheses. This is not necessarily a robust way to reach a conclusion. So multi-regression is the kind of core tool here. If you have nonlinear functions, you can use GLMs there. And then this regularized regression allows us to do this process of variable selection, but this only is really strong in the context of cross-validation. So just be aware of that when you're applying these methods. Okay. Have a good day.